Welcome back, welcome back, welcome back. Sorry about that cutting off. This is a review of the periodic table, part 2. I thought I had deleted everything off the phone so that it would have room for the video, but it held on to it. You know how I'll do that? It'll say, have that file recently deleted. That's what got me. Anyway, so we're talking about the periodic table. We talked about fission, cut it in half, fusion, it's more fun with sound effects, squish it together. Also, the one other thing I meant to say about when we were talking about the families on the periodic table is that the alkali metals over here are the most reactive, and they get more reactive as you go down. So really francium is, I would say, the most reactive, kind of depending on what you're talking about, like, but it just, boom, reacts like that with water. And then noble gases are unreactive. So that's so like even the alkaline metals are more reactive than the alkaline earth metals because they're further over toward the left. I have to make sure I'm going the right way. Left, yes. All right, so now the next thing is being able to look at a column and know what kind of ion it's going to make. Remember, ion is positive or negative charges because we have rubbed electrons on or off. So you can pause the video and see if you can go through and predict what ion these families are going to make. All right, so pause. Now, here are the answers. So this first family here, the alkaline metals, want to lose one electron. So they become, once they lose one negative, then they have more positive than negative. So they become +1 because they lose one negative. Can you see that? It looks kind of little on the video, but it's +1. This family, the alkaline earth metals, want to lose 2 electrons to feel like a noble gas. So they become +2. These in the middle, remember, they just kind of work out sharing arrangements. Sometimes they do become ions, but we're not getting into that at this level of chemistry. But they share, they're the hippies who let the electrons run around free and wild. Okay, these noble gases, they do nothing because they don't become ions. They used to be saying they were inert, meaning they don't react, or they're unreactive, but under extreme conditions, you can actually make them react. So now we don't, now we say they're unreactive or something like that. This next family, you know, is the halogens. And remember, they want to steal one electron. So when they do, they'll have one extra piece of negative. So they become -1. This family, if they can do it, they try to get 2, so they feel like a noble gas. This family would be 3, and this family would be 4. So carbon's family would actually become, if it became, but usually they don't. Usually they do sharing arrangements and do something called covalent bonds instead of ionic, which is transferring electrons, and that's what we're going to do next chapter in bonding. Whew, okay, so, but I'm going to talk about that. I've learned something about carbon ions. They're being used now to treat cancer, and so I've got a couple of practice problems that I'm going to do for you, and I think I did one with a carbon ion just because I thought it was cool and found out that it exists. All right, so how to predict. Ion by column, we did that. So also let's talk about the atom. What is the charge of a neutron? You can hit pause. It's neutral. What's the charge of a proton? It's positive because they both start with P. And neutral and neutron both start with N. Here's the tricky one. What is the charge of an electron? It's negative. Don't get mixed up because its electrons are negative. What is the mass of a proton? Well, we say that its mass is 1. And what is the mass of a neutron? It is also 1. And what is the mass of an electron? It's so small, we're going to say it has none. It has a tiny bit of mass, but so small, it is inconsequential to the mass of the atom. For the mass of the atom, we just add up the protons and the neutrons. Okay, so that was our next thing. Where are they located? So protons are in the nucleus, neutrons are in the nucleus, Electrons are in the orbitals. They're in an orbital outside. All right? Next little thing that's you need to review for the test is if you have an isotope. Remember, isotopes are just different types of atoms depending on how many neutrons they have. So what makes an atom, the atom is the number of protons. So we're going to do carbon and talk about its different isotopes. So isotope, remember, ion is what I have going over here, and it's a charge. Isotope has to do with the mass. Okay, so I have isotopes of carbon, and carbon can be carbon 12, meaning it has a mass of 12. It can be carbon 13. It can be carbon 14. These are different isotopes of carbon. They're all carbon because they all have 6 protons, but they are different isotopes. I'm grabbing my water, sorry about that, because they have a different number of neutrons. All right, there you go. So now let's talk about how many protons, neutrons, and electrons each of these isotopes have. Okay, so first of all, what is the atomic number? The atomic number of each of these. Where do you get the atomic number? Push pause. You get the atomic number from the number of protons, and it's the solid number on the no decimal point number on the periodic table. So for carbon, it's 6. So you probably can't see it, it's real little here, but you've got your own periodic table. Get it out and you'll see it's 6. So the atomic number for all of these is 6. Okay? What is the mass number? Now, you know the mass number is on the periodic table as a decimal, but when you're doing this kind of chart, what you do is you take the mass is the protons and the neutrons, and it's the number, if it's written like this, that's afterwards. So this one is mass 12, this one's 13, this is 14, and that is the protons plus the neutrons to get the mass number. The atomic number is the protons. Okay. Next, it will ask you what are the number of protons, and that one's real easy because it's always the same thing as the atomic number. Okay, the next thing it's going to ask you is the number of neutrons. And how you get that is you just take the mass number minus the protons equals the neutrons. So 12 minus 6 is 6, 13 minus 6 is 7, and 14 minus 6 is 8. So we have, I'll move out of the way, 6, 7, and 8 neutrons. Okay, the next thing I'll ask you is the number of electrons, and I'm running out of board, but it looks like you can see if I put it right there. Yeah. So I'm going to do number of electrons. See if it's showing up on the board. Yeah, it is. Okay, so if it is neutral, the electrons are the same as the protons, and none of this indicates that it has a charge. But if it does give you, if it fills in a number of electrons for you, then you'll figure out what the charge is. So like on this one, I'm going to say that it's neutral and it has the same number of protons and electrons, so it's also 6. For this one, I'm going to say this one is also neutral, so it has the same number of protons and electrons, which is 6. But I'm going to make that one have a charge because this is the one I found out about, that they really make it have a charge now and use it for cancer treatment, and it's an ion of carbon. It's the carbon ion, and what they do is they give it 4 extra electrons. So it ends up with 10 electrons. So the next thing is they want you to write the isotopic notation for it. So I don't have much room here. I'll take down my periodic table. I don't think I need him anymore. Okay, so I'll write it over here. So for carbon 12, you write the symbol. You write the number of protons down here, or the atomic number, and you write the mass up here. If it has a charge, you write it over there. So that's carbon 12. Here is carbon 13. And here's carbon 14. And it has a charge because there is a difference in its protons and electrons, and its charge is it's got 4 extra electrons, so you put a little -4 there. If it has a charge, it goes right there. So that's the complete symbol, or the isotopic notation symbol. You'll hear it called that also. All right, so the next thing that's on the test is the what did the scientists do? So be sure to watch that. I brought something to show you. Oh, but I'll probably show it to you in class because I don't think I can. I need a flashlight. I went down to Miss Raymond's room to get something, batteries and something else, and I forgot something else. It was a flashlight. I'll show it to you though, since I mentioned it. All right, so one of the ways they discovered the parts of the atom, remember we talked about the cathode ray tube, and we talked about the gold foil experiment, and we talked about Democritus and John Dalton. Well, one of the things that they did was something that was like this. Oh, it's working now better. I don't know if you can see it, but there is a little thing that's going around in here. This is a radiometer, and it is not like the real lab equipment that was used, but it is very similar in how they discovered the electron. What they did is they had, in mine, I don't know if you can see, but air can get in it. In the real one that they discovered this with, they had pumped all the air out of it, so it didn't have any atoms in it at all. And then they shot light in it, and the electrons that were in it had both particle and wave nature, and its particle nature was it could make this a little paddle wheel like this spin. And what made it spin was light. As the light kicked off of the paddle wheel, for every action there's an equal and opposite reaction, and it would bang it back. So mine works. I can get a flashlight, and right now these lights are making it spin. And it does it. The light can make the little paddle wheel spin, like how they used to discover electrons. But mine, of course, is cheap and not the real thing with all the air pumped out of it. So mine has other things affecting it, like temperature and air currents. So anyway, but I'm sure there's a video on YouTube of a real one doing it. But I like my fake one because it does it, even though it models it. It's not really it, it's a model of it. All right, so the next idea is you got to know the scientists, and that'll be a matching part. And then you need to, and what they did, and make sure you do your scientist paper. I haven't gotten many of those turned in yet either. So I'm looking at your progress, and a lot of you are not doing your digital learning. So make sure you get it done. It's all going to count. I don't want digital learning to hurt your grade, because right now most of y'all have great grades in here. All right, so our next thing is a math problem. Yay, because math is great. I'm saying that with firmness, so you start to believe it. Math is great. All right, so the math problem has to do with abundance, percent abundance. So I have some different isotopes of silicon. I've got silicon 28, I've got silicon 29, and I've got silicon 30, okay? And for each of these, even though the mass comes from, there's really a whole number that comes from the protons and the neutrons added together, they have like this scientifically found mass that's slightly different. And it has to do with E equals mc squared and some other stuff like that. But right now, we're just going to accept that this has a slightly different mass in real life, and it's because of that relationship between mass and energy. So here are the masses, if they're very precise, of these 3 isotopes of silicon. Okay, and then we have the percent abundance. This one is 92.23%. This one is 4.67, and this one is 3.10. So how you do these problems is just like all those other problems we did. You multiply, and you have to change this to a decimal by moving the decimal place over 2 places. And if there's nothing there, you have to add a 0. You have to augment a 0. So 1, 2, there's my new decimal. So on my calculator, I'll do this whole big number times 0.9223, and then I'll do it times that and times that. So this equals, when you do that on your calculator, 25.803197. This one equals 1.353202, and this one equals 0.9291867. Then what do you think we do? We multiply, then what do we always do? You're right, we add them up. We add them up, and it equals 28.0855 ... So it approximately equals, we'll say 28.1. So that's how you do it. You just take the masses, multiply it to the percents turned into a decimal, and then add them up. So just like those, very, very similar to those other problems. We're going to do a slightly more complicated problem next week with isotopes and abundance, but I'll walk you through it and for a lab that we're doing. All right, and then so there's going to be a couple of these on the test. There was I can do one more for you because you have 2 of them on the test, so I'll do 2 here as long as my video doesn't cut out again. As long as my memory doesn't get too full and my video cuts out. So here's another one, carbon 12 and carbon 13. Now in this problem, we know that there's really a carbon 14 too, but this problem said that it's so rare that you really don't even have to do it. It's too little. And so carbon 12 has a mass of 12, and carbon 13 has a mass of 13.003. Remember, they're slightly different because they equals mc squared. And we're going to multiply it times its abundance percent written as a decimal, so it's 99.3%. So we write it like that. We take the I said 99, I wrote 93. Oop. Forget that I did that. Okay, so it's 99.3%. You move the decimal place over 2 frog hops, and then this one is 0.7%, so it's 0.0070. We multiply them, and this one is 11.916, and this one is 0.091021. We add them together, and the mass ends up being 12.0070, something like that. All right, I think you can do those. They're very similar to the other problems we did. We're just, so we're having them again. All you do is multiply the mass times the percent, add them up. So that's the test. I think y'all are going to do great on it because we have been over this probably more than anything else we've done this year. So make sure you get all that digital work done. Play your plasma game, write your atom paper, do your build an atom simulator. Know that I have this teacher ability where I can go in and manage those, and I can see what you've done. So I know if you've done it or not. So make sure you spend time on those things and have fun. And can't wait to see you guys next week, and we'll have the test and you'll do awesome on it. All right? Science is great.